Diophantine equations would be the topic that we have for our third contest for math team this year. Diophantine equations we will introduce a little bit later, but in fact, to really understand Diophantine equations and how to solve them, we're first going to have to talk about modular arithmetic. Modular arithmetic, you can see right here, is just a very special type of arithmetic that involves only integers, no decimals, no fractions. It's based on congruence or equivalence of the remainder of a number when it's divided by a given modulus. The abbreviation for the modulus is usually MOD. So if we're in mod 5, in modulus 5, if you think about it, when you divide by 5, you only have a number of possible remainders. It's like going back to 3rd or 4th grade, where you write that big R with your long division. You'd either have a remainder of 0, 1, 2, 3, or 4. So, for example, when you look at 22, you can see we use 3 bars instead of 2. 22 would be equivalent to, well, let's see, if we were to divide by 5, 4 times 5 is 20. And if we went back to 4th grade, you'd say that this is 4 remainder 2. The fact that we have this remainder 2 is actually the answer that we're going to arrive at. 22 would have a remainder of 2 in mod 5. So let's take a look at a few more examples. Let's just say that x was equivalent to 37 or congruent to 37 in mod 6. Well, I think very quickly, even without having to do long division, you could know your answer. I'll use the long division right now, though, and say that 6 goes into 37 6 times. You'd have a 1 left over. We'd say that x is congruent to 1 mod 6. Now, I'm also going to introduce a parametric form for this answer. We could say also that x is equal to 1 plus multiples of 6. We could say plus 6t, where t would just be integers, 0, 1, 2, 3, and so forth. What I'm really getting at is, if t is equal to 1, we'd say x is equal to 7. 7 would also have a remainder of 1 in this situation. If t were to equal 2, 2 times 6 is 12. 12 plus 1 is 13. 13 is going to be another solution to this equation in the sense that we could say that you'd have the same remainder, a remainder of 1. Let's jump over here for x congruent to 23 mod 17. So very often kids even wonder if they could just subtract 17 repeatedly. And you actually could. You could say, well, what's 23 minus 17? That's really saying that 17 would go into 23. If we were to do some work, we'd have a 6 left over. 17 would go into 23 once, and we'd have 6 remaining. So we'd say x would be congruent to 6 mod 17. This is a great solution, but let's also write this parametrically. X is 6 plus all multiples of 17. And that would be another way to write this solution down. Taking a look at 137 in mod 11. Well, whether you know your arithmetic facts, that really can speed this whole process up. We know that 11 goes into 13 once. Bring down the 7, we could say, well, 11 goes into 27 twice. And without too much work, we'd see we have a remainder of 5. This would be x is congruent to 5 mod 11. And how would we write this parametrically? Well, we'd say it's 5 plus 11t. The parametric answer is actually going to be used more frequently when we get to the actual Diophantine equations. So I think that's important for us to see. This is brand new. You wouldn't have learned this in Algebra 1, Algebra 2, AGT, or AMA. As you're looking at this type of a new type of a property of numbers. I just want to point out that you could say A is congruent to B in mod M and C is congruent to D mod M. You can add to get A plus C would be equivalent to B plus D. You could subtract. You could multiply. You could raise to positive integers. Can you divide? Actually, you can, but you have to be very, very careful when you divide. If you have A is congruent to B, you can divide by G, but it's possible that your mod would change. Your mod would be M all over the greatest common divisor of M and G. We're going to actually look at some problems like that in just a moment. Let's immediately go to right over here where we're solving some equations. This is definitely going to help us out considerably. Let's take a look at example 1 when you're thinking about solving for x and you can think mod 13. Here's the thing. We want to get a 1x. Every time you've solved an equation, you'd have a 1x. The big question is, how do we get a 1? Well, we have to have a remainder of 1 from 13. So we'd have to be one step bigger than 13. So if you look at 13, the multiples of 13, 13 times 1, 13 times 2, 13 times 3. If we were ever one step bigger, in other words, if we had a 14 or a 27 or a 40, this would be a remainder of 1 when we divide by 13. So I'm looking right here. I don't like seeing that 7, but I do realize that I could multiply both sides by 2. Now, if I multiply both sides by 2, I'd get 14x, and over here I'd have 16 mod 13. But here's the thing, 14, when I divide by 13, I'd have a remainder of 1. And 16, if I were dividing by 13, well, you could even subtract. You can see that you'd have a 3 left over. This would be x is congruent to 3 mod 13. Let's write this out parametrically. X is 3 plus 13t. Let's take a look at example 2 just for a moment. As we're looking at example 2, I think this gets to be a little disconcerting as we see mod 29. And certainly we can begin to look for multiples of 29 and ask if we'd get one step bigger, such as if we were at 29, we'd be at 30. That would be a remainder of 1. And, if we were looking at, 29 doubled, you might be thinking, well, that would be 58. And if we were one step bigger, that would be 59. And, you don't have quite as simple of a situation multiplying the 16 by something, but tell you what, how about we just double both sides? Now, that might seem rather strange at first. You might think, why on earth are you going to multiply by 2? Doesn't seem to help you out. 27 doubled, of course, will be 54. And, as we're looking right here, you can think, well, how is this helpful? Well, look at 32. It's 3 steps above 29. This would be a remainder of 3 if I divided that out. And likewise with 54, you can think, well, with 54, if you even subtract 29 right now, and you'd have to borrow, you could see, well, we'd be at, 25, evidently. You can see right over here, this would be a remainder of 25. You could think, well, how in the world has that helped? Is this helping whatsoever? And it really is. I'll tell you why. When you look at 3, I can get up to 30 pretty easily. I can actually multiply both sides by 10 now. And I'd get 30x would be congruent to 250 mod 29. And at this point, you can see that the 30 is just one step above. This would be equivalent to a 1. And right now, we're reached our solution. So that's really good. The 250, of course, as you begin to wonder, how to break this down, you can ask yourself, well, how many times would 250 go in to 29? And we can try to find that remainder. And you could even work backwards, by the way. Here's another way. Obviously, you can just do long division. But you could see that 29 times 10 is going to be 290. That's a multiple of 10. If we were to, just work backwards, continually subtracting 29, that's like subtracting 30, but then adding 1 back. That would be at 261. And if we were to subtract 29 again, well, imagine that you subtract 30 and you add 1 back, you'd be at 232. Why am I doing all this? Well, this would be a multiple times 10. This is a multiple times 9. This would be a multiple of 29 times 8. But that 232, right now you can, pretty much see that how far is it from 250 to 232? Well, it doesn't take much for you to see it would be 18. And could you have just used long division to work this out? Of course you could. Of course you can work that all out, and that would be fine. But that's no doubt. Hold on. Yeah, with the long division, of course, it would yield the same thing. Let's write this out parametrically also. X would equal 18 plus 29t. All right. Tell you what, let's begin to get into this division property. And like I said earlier, I think sometimes we look at a 22x and a 4 here, and immediately we can think, well, isn't it possible to divide out, say, a 2? And it is. It really is something worth noting. We can divide out that 2. And as we do that, you can see that we'd have 11x would be congruent to 2. Now, the big question is, would the mod change? Let's look at the greatest common divisor of 2 and 29. That's just a 1. In other words, 2 doesn't divide that modulus. What does that mean? When you are dividing by a number that doesn't divide your mod stays the same. That's really what this property of division is saying right here. If the number you're dividing by and the mod itself don't have a common factor, in other words, that number doesn't divide in, the GCD is 1. And that, thankfully, is going to make the problem so much simpler. What we now can do is, realize that as we're looking at 11 and 29, you could ask yourself, well, what are some of the multiples of 29? 29 times 1 is just 29. 29 times 2, you can see we began to do that off to the side. That was 58. By the way, that's just like continuing to add 29. If you add another 29, you'll be at 87. That's 29 times 3. But look, if you were to go one step higher, that's 88. That is actually where we want to go. I'm going to multiply both sides by 8. And here we'll get 16. And wonderfully, as we're just going to look at this just becomes a 1x. And we're done. So wonderful to get to this point. X would be 16 plus 29t. Okay, we're going to stop right here and have to finish up the rest. Number 4 has a very special, different type of a property going on, but we'll talk about that soon.